Thanks, Peter, for the nice presentation, and welcome everybody. Thanks for your time being here. So yes, today I'm going to present ALP, which stands for Adaptive Lossless Floating Point Compression. But if you look closer in this slide, maybe you get the why of the name also. Let's see if you can get it. So, what is going to be the outline for today?
Should have had 2 A's. It will be very good.
So first I'm going to introduce you to floating points. Then we're going to dive into what has been done in floating point compression. And then I'm going to present to you ALP. To finish with some closing remarks, and last but not least, some time for questions. So without further ado, I think we can start. So this right here is a real number. Some of you may call it decimal number. Looks very nice. So how computers do represent these numbers? Well, they use something which is called floating points. And today we're going to be focusing in double precision floating points. So how do computers represent these numbers? Basically, there are 64 bits, which are divided in 3 main parts. The first bit is to represent the sign of the number. The second part is 11 bits that represent something called an exponent. And the last 52 bits is something called fraction, or also called mantissa. And then to get that number, you have to plug in those bits into this kind of weird, scary formula right here. And then you get the number. So let's see what happened if we try to represent this number as bits. You will get this bitwise representation. But if you put these bits into the formula that I just showed you, this one, you'll end up getting this number. So then what happened here? Why I cannot represent that number exactly? And the problem is that this number is not a real double. So you cannot represent in a computer as a floating point this literal as that's the exact number that you see there. And that's why you get this number. So that's why floating points are kind of hard to compress, because there's a lot of precision errors that you get when you treat these numbers. And this translates into that you cannot apply encodings that depends on arithmetical operations like delta or frame of reference. And also you cannot bitpack them, because as we will see in just a few moments, there's a lot of randomness in these bits, in these 52 bits of the fraction, even though the numbers look very similar between them. So we'll see some examples later. And also other compression mechanisms, as the dictionary or random encoding, only works in specific situations. For example, when I have a lot of the same numbers repeated in the data that I want to compress. So this is why floating points are kind of hard to compress. But there are still some commonalities in the data, in this bitwise representation, that create some opportunities for compression. So for example, let's take these 4 floating point numbers that you can see right here. And this is their bitwise representation. So at first it may seem like random bits between them, but if we compare the 3 numbers that follow the 0.2, we can see that a lot of their bits in their fraction are exactly the same. So this is very interesting, and not only in these trailing bits, but also in the front bits. You can also see that they are repeated with the first number in the example. So this creates opportunity to apply a very interesting operator, which is called the XOR operator. So how does the XOR work? Let's say, for example, we have these 2 numbers, 0.2 and 0.4. What the XOR operator will do is that if we XOR 2 numbers, the resulting number will be a bit 0 if the 2 bits are equal, and a bit of 1 if 2 bits are different. So this will be the result of the XOR, and it's a beautiful chain that can be very well compressed using some methods. But this crazy amount of zeros is very useful when you want to compress data, obviously. But when you start getting more precision into your doubles, things start getting a little bit trickier, because, for example, these 2 doubles that have this representation, you can see that there is a lot more randomness in the trailing bits. And in fact, in this case, only the front bits have some kind of a similarity. Therefore, it's the chain yielded by the XOR will not be really as beautiful as the previous one. So In few words, the higher the precision of these numbers, these doubles, and the more entropy they have between them, there are less compression opportunities for the XOR operator, as we have seen in this example. Regardless, there has been a lot of approaches in the last few years that have used very cleverly this XOR operator to compress floating points, and they have achieved really nice results in terms of compression ratios. The first one, or not the first one, but the most relevant one is called Gorilla, which was developed inside a system of Facebook. And basically what they try to do is that, okay, they XOR in a stream of data, they XOR one value with the previous value, and then based on the resulting chain of bits, they compress these zeros, trailing or leading zeros, in such a way that they optimize how the data is compressed. So I'm not going to explain in detail these algorithms, but just the main idea. They analyze the chain of bits resulting from the XOR, and they compress it in different ways, depending on how many leading or trailing zeros they are. Then after Gorillas, Chimp 128 was developed. So basically what they do was to improve Gorillas. They improved the compression cases based on observations that they did in the data. And one of the interesting things that they also did was that they do not only XOR with the previous value in the stream, but they look into the 128 previous values to that value to find the best match for the XOR. So the number that will lead to the most beautiful compressible chain between all of these values. So this effectively improved compression ratios compared to Gorillas. And then we have Petas, which is a variant of Chimp 128 developed by Dr. B. And the interesting thing is that Petas, it does not have cases. It's just only one case. So this kind of make it a bit faster. And the compressed bits are stored in a byte aligned way. So you don't have to treat with bits offsets when you are decompressing the data, which makes the algorithm faster. But the compression ratios, since we only have one compression case, the compression ratios kind of reduce a bit. And very recently, a new schema called ALP has been released, which is very interesting because they use a lot of math shenanigans in which they say, okay, we're just gonna remove the trailing bits, we're gonna remove this randomness, and then at decompression time, we're gonna recover that without losing information, which is kind of crazy. And they indeed increased compression ratios, but at the expense of a very, very slow decompression speed, especially, and compression speed also. So these schemas are really good.
Can I ask a question halfway, or do you want it to the end?
I think at the end,
Okay.
a little better.
Yep.
Yes. So these schemes are really good, but at the end, they have some shortcomings, right? So, for example, Chimp 128 have data dependencies because you have to look into one of the previous values to be able to decompress one value. Since they have branches, they are not very kind of CMD friendly. Because as I say, they have multiple compression and decompression cases. So this ends up in branchy code, especially in the case of Gorilla and Chimp 128. And as an example of this, these are all the cases, all the if conditionals that you may find in the code of Chimp 128. So yeah, not very CMD friendly if you really want to be fast in the compression and decompression. So the question is, okay, can we do better than all of these approaches that have been developed in the last years? And to answer this question, let's remember again why floating points are hard to compress in the first place. So they're hard to compress because we can apply mathematical things, arithmetic operations in them to be able to do delta 4 encoding, which have been demonstrated to achieve very good compression ratios in some data. And we have the problem that the fraction bits are very random, even though the numbers are very similar between them. But what if we could convert these floating points back and forth without losing information to integers? If we could do this, then we could apply encodings like delta 4 or bit pattern, which are really good in integers. And also we remove the fraction bits randomness because right now we're treating with integers instead of this floating point representation. So let's try to do that. Let's see how that goes. So let's say we have this number, which is the same number that we have in all the examples that I have shown you since the beginning. And well, the first intuition to convert this number into integer would be to do the following, to multiply by a factor of 10. So it seems that it worked. So now we have a beautiful integer, which is very compressible. And well, let's try to recover now the original double, right? Because we have to go back and forth without losing information. And the first glance, the only thing that we have to do is just do the inverse operation, 10 to the factor of -4. And this will effectively give us the same number that we started with. The problem is that this is not correct. Even though it seems very, very simple and good, it's not really correct. So what is the problem of this procedure? Where do we fail? Let's start over. First of all, let's keep in mind that we're not treating with this number exactly. We're treating with this number. Let's remember from the first example that this is not a real double. The real double is at the right. So this means that we can not only do the multiplication, we need to do a rounding first of all. So yes, we need to do a rounding because it's not an exact multiplication. So to get an integer, we need to do a rounding. And then when we do the inverse operation, here's when things get kind of tricky. Why do we get a different number from where we started with, if everything seems correct? And the problem is here. So the problem is that this number is not exactly equal to 0.0001 because of the same reason that we just saw in the beginning. This number is equal to this. So this error introduced into this multiplication is what basically destroys our key idea behind this, that error in this 10 to the power of -4. So how can we solve it? Let's try to do it. Let's go back to square one. So we have our number. What if we use a bigger exponent? Let's say 10 to the power of 14. So then we got a bigger integer, and then let's try to do the inverse operation. Well, here we have indeed our same number. What happened here? Why in this case, only by increasing the exponent it works? The thing is that right now, 10 to the power of -14 is such a small number that the error is so small that at the end we end up getting the same original double. And this happens because the closer a double is to a 0, the more exact the representation can be. And this is why this works and exponent 4 does not work. The idea behind this was introduced in pseudo-decimal compression. So this whole idea of converting doubles to integers using exponents. So now we have converted our original double into two numbers, an encoded integer and an exponent, 14. So we have successfully done what we have set. But this number looks kind of ugly, right? Why will we need to store all these zeros? So here I can see, okay, they are kind of unnecessary zeros. Do we really need them? And the answer is that not really. What we have discovered is that this number, this encoded integer, can be further reduced. For instance, let's go back to our number. And now let's say we want to reduce that big number. What we do is that we apply a kind of reducing factor in which, okay, we have our big integer resulting from this, and then we reduce it with an additional multiplication. Now we got a smaller integer, and now let's reverse the operations, and now we do end up getting the same double again. But why this works, and let's keep in mind that this is the same example that does not work with 10 to the power of -4. And it's again because the error here is so small compared to this number, this result of the multiplication, that at the end the rounding does its job to round the number. And here the error in this, and here this reducing factor here does not introduce any error because it has an exact representation, because it's not really a double, 10 to the power of 10. And that's why this works. So, okay, so now we have our original double, and now we have three integers, but then you're going to be asking, okay, Leonardo, we went through all of this, but we have three numbers. Isn't this really worse than having just the double of 64 bits? Because now we have three integers. Isn't this worse? And also, how do you find that exponent and reducing factor? Like right now, I have just given that to you, but how do we find that? Really, is it hard to find? Is it easy to find? So the answer is that we have found some in-vector commonalities, and here we define a vector as, let's say, 1,000 consecutive values in a data stream. We have found some in-vector commonalities so interesting that we discovered that only one exponent and one factor works for an entire vector. So for a group of 1,000 values, we don't need one different exponent and factor for each of the numbers. We can only use one for all of those numbers. So then that translates in a lot of safe space. And finally, the search space for this exponent and factor is limited. What I mean is that we do not have to search through all the possible exponent and factors combinations because we have discovered that this search space is limited. For instance, we have done analysis on some data sets, and we discover in this plot here, you can see the distribution on how many pairs of exponent and factor are needed to achieve the best compression in these data sets. And as you can see in most of them, for all the data set, we only need one combination to fulfill all the values inside of the data set, which is kind of very interesting, right? So now it comes to UP. Leveraging all of these ideas, we developed UP, and as I have just mentioned through all the presentation, the main idea of UP is to encode doubles as integers in a per vector basis. So we're talking about, okay, we're gonna be thinking in vector basis, not value basis. And for each vector, we're only gonna use one factor and one exponent. And then the integers are gonna be further encoded with frame of reference compression. Since now we have small integers, it's very easy. And another key idea of UP is that it fully fits into a vectorized execution. It's very fast because it's built on different codes, and it uses fused kernels of compression. We also do not use the built-in rounding function. We do a trick to round doubles in a fast way, which we take advantage of a limitation of doubles in which from certain range, they cannot possibly have a decimal part. So we do an addition and a subtraction to take the doubles into that range. So the decimal part is removed, we take them back, and then we have our rounded number without using the standard function library, which is slow, nevertheless to say. And UP speed also stems from the fact that we use fastlength primitives. So what is fastlength? Fastlength is a project developed here in CWI, which is an optimized data layout that allows compression schemes to use all CMD lines. As a result of this, we can maximize the CPU usage work. And also, it's very interesting that fastlength is built upon scalar codes that can auto-vectorize in an efficient way. And here are the results of UP. Before diving into the complexity of its implementation, we wanted to show you the results that we have. In this plot, you can see three variables. In the x-axis, you can see the compression speed. Y-axis, you can see decompression speed. The higher is better. In this case, because the speed is measured in the amount of values that can be compressed or decompressed in a CPU cycle. And then in the plot, you can see written the compression ratio that we have achieved, in which higher is better. So the only scheme that is better than us in compression ratios is CSTD, which is a general purpose compression scheme. But in terms of speed, as you can see, UP is very high in the plot. And let's also take into account that this plot is in a logarithm scale. As you can see, we beat all of the other compression schemes that I briefly mentioned a few minutes ago. So now we go into the kind of boring part. How do we find the exponent and factor per vector? Because right now I have just told you, okay, we use one exponent and factor per vector, but how do we find it? And this is kind of also something that we did. Basically, we do a two-level sampling. So we sample the data. In short words, we sample the data. We do so in an efficient way because we first sample row groups and then we sample vectors. And how do we do this? Here's a data set. So it's just a stream of those. And it is in the representation of a row group and vectors. So as you can see, what is a row group? A row group is just a bunch of vectors, in this case, 100 vectors. And each vector is 10,024 values. So what we do is that we first sample row groups. So we take the row group, and then we take 8 equidistant vectors from the row group. And then from each vector, we do not take all the vector, but we only take 32 values for each vector. And then for each one of these samples of vectors, we find what is the best combination of exponent and factor. And what do I mean by best? Best is the one that achieves the smallest integers and the one combination that can be used to indeed be able to convert them to integers and recover the original doubles. So this will effectively return us one exponent and factor per each of the samples. And then since these combinations may be repeated, as we show in some of the data sets, there's only one combination that works for all the vectors. We just choose the top k combinations that appear the most, in which k for our experiments was just 5. So cool, now we have only 5 combinations instead of 190, which is the entire search space. And now with this, we go to take samples at a vector level. So we take the vector, we take a vector level sample, which is 32 samples from 1024 and kind of around 3% roughly. And then we see which of these combinations works the best. And let's keep in mind that if there is only one combination, we just skip this part, because if there is only one, we don't need to check which one of these works better for the vector. And then we're gonna get our magic exponent and factor number for the vector that we want to compress. And then we go to the compression of that vector, which roughly will go as follows. So we will take each of the numbers. Of course, we have to compress each of the numbers. So we take them, we apply the formula that I just explained to you a few minutes before. So it's basically a multiplication with exponent and the reducing factor. And then we get the integers encoded, basically. So here, as you may imagine, we do have to make sure that we can recover the original double, because we don't want to lose information. So we do this because there can be some outliers in the data for which that exponent and factor does not work. So we need to take into account this. So that's why we do this comparison. It's basically saying, can we recover the original double or not? So in this case, we can, but let's say that we cannot in the second number. So what do we do in that case? We store that as an exception, and we say, okay, this double, we cannot compress them without losing information by using this factor and exponent. So we store it uncompressed as an exception. And yeah, then we continue. Here we find another exception, and finally we end up with all the encoded vectors, which are now integers. And now that they are integers, we can apply frame of reference to make them smaller. And finally, we end up with a vector of integers, which ideally will be very small, and exception vectors, which ideally will be empty, at least in most of the data sets that was the case, and one exponent and one factor. And this is how we achieve compression. And then we continue to the next vector. And decompression, it's very straightforward. Decompression, we just need to reverse the frame of reference. We call this un4, just decoding the 4. Then we have to decode the integer vector into the doubles. And how do we do that? It's just 2 multiplications. 10 to the power of the factor times 10 to the power of the minus the exponent. That is a store with the vector. So this is also why decompression is really fast, because it's only based on 2 multiplications, nothing more, no if, else, nothing basically. And then if there are exceptions, we patch them. So we reconstruct the vector taking into account the exceptions. Now, the interesting thing is that what I have just told you does not work for all doubles. There are some doubles which have a very high precision, let's say 16 decimals of precision, in which this method does not work. Because as you may imagine, for this method, we're storing all the information as integers. And if a number has, let's say, 17 decimal positions, you need to store that information, and it will not achieve any compression on those that have a very high precision. So what do we do in these cases? In these cases, ALP adapts to these doubles. And how does ALP adapt? Well, basically, we take advantage of the front bits of the doubles. Because even on these very hard doubles to compress, we have found that there are commonalities in the front bits of these numbers, which is very interesting. So what we do in these high precision doubles, let's say we have these doubles right here, we detect a position in which all the front bits are kind of similar between them, and we split them. We just split them bitwise, and then we're left with a left part and a right part of these numbers. The right part, which is the mantissa, we deem this as uncompressible because it's so random that we cannot find any pattern to do compression, so we just bitpack it. And the left part, since these values are similar between them, we use dictionary compression to compress this. And by doing this, we achieve better compression than all the other methods in these data sets. And we call this ALP-RD for ALP for real doubles. So before finishing, I want to talk to you about the results more in detail. So we tested this on 30 data sets, which were previously used to benchmark the other algorithms, which I talked to you in the beginning. 13 of these data sets were time series data sets, and 17 were non-time series data sets. And here are the results for compression ratios. So as we saw in the first figure of the results, we're only beaten by CSTD, but after that, we are better than all of the others compression methods specifically tailored for floating points. And for some of them, we are better by a lot. For example, against betas, we are a lot better, right? Only ELF is kind of comparable to us in compression ratios, but as we will see, ELF is very slow. So when does other schemes do better than UP? Other schemes do better than UP when perfect XORs can be found. What is a perfect XOR? It's when values are equal. So when values are equal and you XOR them, you end up with 0. And 0 is a very compressible number. So high percentage of equal values. In these cases, other schemes are a bit better than UP. And as another note, ALP for real doubles achieve the best compression on these high precision decimals. And this is the results of speed. And this is a very interesting comparison because we were faster than all of them. And that's why we could put in this table a column in which we show how much faster we are than these other schemes, right? And there, here you can see some of the things that I was talking about, that this algorithm ELF is very slow on decompression, right? Also, pseudodecimals is very slow in compression compared to us. Like we are 251 times faster, and we are also faster than CSTD. And yeah, it's very interesting results. And yeah, basically that's it. So as a summary, UP has shown to be faster and better than current floating points encodings. It's fully tailored to fit into vectorized design, seamless-friendly code, so we avoid as much in the main encoding process that there are no branches and no if-else. Also, thanks to fastlines, we can build it upon scalar code that auto-vectorizes. So I say thanks to fastline. We also use fast rounding, which was really important to achieve a lot of speed. And also, we don't use division. So this is kind of also important because division is an expensive operation in some instruction sets architectures. So we avoid division. That's why we do everything with multiplication, as I showed in the beginning of the presentation. And as future work, well, we want to test UP with cascading encoding, which is when you cascade a lot of schemes, compression schemes, one after another. We also want to adapt UP to different floating points precision, like 32, especially 32-bit precision. Also try to test this on GPUs. Integrate UP to the fastlines projects, and we also want to test it on end-to-end benchmarks in the query processing engine, which we're currently working as of now. And thanks for your attention.